Everybody.
Hi. Hi, friends.
We're here.
This is a group of friends talking about boards, electronics, music, whatever comes to
there
mind.
was
Pyrotechnics.
interesting stuff in the Discord channel this week.
Yeah. It turns out that's working.
So yeah, it's too bad whether it's not I don't know of an easy way to tie Discord chat to the to the Google chat or anything like that. I've been looking. So Dave Adams says good afternoon on Google chat or YouTube. I mean,
Dave, Chris.
Hey, Chris.
Hi, Chris. Hope you're all doing well and ready for a nice weekend. I have some cool news.
What is it? Whoop, we lost you, right? You went to tell us the cool news. You're still lost. Okay, you're back.
Yeah, I'm cutting out. I'm going to do internet speed here.
Well, I notice it's right at 2. I assume that maybe one of your kids gets on a class or something. Hey, Robert. Well, we lost Ben there for a little bit. Figure he'll rejoin us here shortly. I see him moving.
Yeah, I find my internet
back.
picks up again whenever I try to run a speed test. It's like AT&T's watching for me to hit that speed test URL, and then they flick it back on again.
So I'm
very much a conspiracy theorist when it comes to internet speeds and telecommunications companies, because the area I live in, I can get AT&T and Cox, right, and they know it's kind of a monopoly. So and it would cost me $2,000 a month for what you have, the equivalent of what you have, Bill.
Right.
So I need to move somewhere where I can get that. Or tether to my phone.
I noticed one time when I ran a speed test on my FiOS that my phone got a text message going, "Are you?" And my phone happens to be, Verizon also. So they text messaged me asking me if I was having troubles with my internet. It's like, wait a minute, you took my phone account and you took my internet account and you correlate them, watched what I was doing, and then DM'd me because I was doing a speed test. It made me want to quit everybody. Go live in the mountains somewhere. Yeah. Because I'm already paranoid. So I'm sorry, I cut you off there.
Yeah, but when you're an electrical engineer and you work professionally or have worked professionally in networking, you currently do, and I did probably 17 years ago, I was working in networking. And you've seen what goes on behind the scenes.
Yeah.
Right. You're going to have a paranoid view of these things.
Well, I'm in network security. I get paid to be paranoid.
Yeah.
So it's and you know the old saying, just because you're paranoid doesn't mean they're not out to get you.
It, of course, doesn't help that I'm a Sagittarius, and by nature we are paranoid sorts of people.
Well, I love Steve Martin's line, I'm a feces.
What was that from The Jerk or The Lonely Guy? What was that movie called?
I saw it first on his stand-up, and he just said, like the Tonight Show, and I'm a Pisces, so, anything that sounds like Pisces, it came out feces. It was pretty cool.
We're a member of the human feces.
Yeah.
As opposed
there you go.
To species. This is not...
That would explain so much about middle management. So what do you want to talk about today?
Well, you have something that looks rather cool right there. It looks like a live view of a VNA. Is that what that is?
That is a live view of a VNA.
Which VNA is it, though?
This is a
is it a USB VNA and you've got it runs on software, or is it
yes,
an actual VNA that has a VGA output?
No, it's a USB VNA called a TTR506A from Tektronix.
Oh, okay. So that's a nice expensive
It's small, yeah, but it does 6 gig. And
wow. What does
if we
those cost you?
I don't rightly remember, to be honest. But so if I back up a little bit, what I'd gotten into was home radar was one of the things I was playing with before the pandemic. And I posted a link in Discord under the topics. If somebody wants to repost that to Google, that'd be great, or to YouTube. I can't tell the difference anymore. YouTube. Where a guy went into the math behind a coffee can antenna. And what I did was I worked through all the math, found one of the low frequency cutoffs, the high frequency cutoffs, and then true to my form, I went and found a better coffee can. Hang on, I'm having trouble moving get us both in the image again.
Yeah, I was
so
dropping
what
out
I ended
there
up
again, and I realized I had to kill a bunch of other things too.
Oh, cool.
So
cool.
Sorry
well,
about that.
I like it when there's reasons. So basically, instead of a coffee can,
to the VNA though, right?
Yes, but I wanted to show what we're seeing on the VNA. So what it is instead of a coffee can, which was a compromise, but this stuff can be fudged a little bit, I went to a specialty bottle and found custom containers and made my own. And I think it should work better. I did the math that says it should work better. And what we end up with is a circular waveguide with a small piece of copper in it hooked to an SMA port.
How do we think the metal, I don't know what you call it, a flange or lip on the end, will that have a profound effect, or does it not really affect the overall diameter?
I tried to make sure it made good electrical contact, and as always, it's the skin, right, that has to make contact. So I made sure it was kind of burnished underneath the SMA when I attached it.
Right.
So that I get good metal-to-metal contact.
I don't know what to call it. That ridge around the end, though, where the lid goes on.
Oh, yeah.
That's what I was thinking of.
Oh, I gotcha. Yeah, I would have no idea what the actual impact. I would assume it'd be 1%, right?
Okay.
That'd be my guess. Given that the original coffee can was off by a couple inches, right?
Oh, wow.
Yeah, and one of the frequencies actually got very close to one of the corner frequencies, but it's all good in hand grenades, right? And when you're making up stuff like this. So, and then the center of this, let me turn it so you can see it. The center of this is just a piece of hollow copper wire soldered to the center of the SMA connector. And this one has not been trimmed for length, but I did trim one for length, and that's what's on the VNA. So what this is I hooked my VNA, whoops, wrong one. I hooked my VNA right up to another one of these. And what we see as I trimmed it, you can see this, let me see if I can get the mouse on here. This point here where it comes down a good 20 dB, we start at 0. This started all the way up here, and as I trimmed it, actually I don't know where it was now I think about it, but as I trimmed it, this whole area came alive. And now I can wiggle my hand in front of it, and it's actually acting as a radar, just using the VNA as a signal source. So, and we see some harmonics and stuff going on and things, but yeah.
So you're looking at, so just to describe this, you're looking at S11. So
yes, I am.
S11 is the total reflected power from the antenna and the system you're hooked up to, right?
That's right. That's right. So and go ahead, talk about VSWR or the reflected power, if you would.
Yeah. So, okay. So VSWR stands for voltage standing wave ratio, and if you have any, so how that's basically came about is if you have any signal and you have a wire or transmission line to send it down, it has a certain impedance, and you have a source impedance, and to get maximum power transfer out the other side, you need to have completely 100% matched impedance of load to transmission line to source. And so in RF, we typically work with 50 ohm loads. And what happens if you have a transmission line and an open circuit at the other end is all that energy has nowhere to go because you have no load. So it reflects back up the line, and it reflects in phase. So you can imagine this exact same phenomena happens in mechanical systems as well. So if you have water in a trough and you pulse one end of the trough, you see a wave go down, and if the end of the trough it is just a wall, it's reflected back up the trough. You see the wave comes back up, and then you can hit the wave trough at a certain resonant frequency. You can get waves going like this, and that's your standing wave. And the same thing happens with the current in a signal traveling down a wire or down a waveguide. And so you get these nodes when you have no load, or a short circuit is also no load, but it reflects negatively.
I've got an open here. Yeah, I've got 100% reflection right now.
All the energy is reflected back up because it's got nowhere to go. And in signal analysis at RF, we use S parameters. We haven't got time to go into S parameters. But all the engineers on the call know what S parameters are. But basically, it's like you have this thing. You treat it like a black box. You put a signal in. You measure what comes out, and you measure what's reflected, and that tells you about what's inside the black box. And those are your scattering parameters. And so S11 is the scattering parameter that is the reflected energy out of the first port. And of course, we have S parameters because a lot of systems have multiple ports, multiple inputs, multiple outputs, and it starts to get super complex and need a lot of algebra and matrix math and weirdness.
Yeah.
But the bottom line is S11 means if you have a really well-matched system, you get very little energy reflected back. So a VNA sends something down and it measures what comes back, and that's your S11. And so here, what you're showing, Bill, is that above what's that third frequency line?
That's 3 gig is right here. 3 gig is right here. 2 gig is right here. So I've got it right kind of happening in the ISM band here at 2.5 gig.
Yeah. So that means your antenna is tuned to 2.5 gig, and you still have some reflection because it's not perfect.
Some. And I can put a cap on it, and it'll reflect a bunch more.
Yeah.
But
or you could put.
What's interesting is this is all the energy that left because it's tuned. You know, it's an interface to the air, right?
Right.
And this much energy, everything below zero here. Let me get on the right screen. Everything below zero is right here. It's hard to see on this.
Yep.
But all of this energy left in the 2.5 gig range and went screaming into my basement here.
Yep. So the antenna is radiating. Make no mistake.
Yes. Yeah.
And
it's already a radar. I can wave my hand in front of it and see things.
Yeah. Actually, there was a really deep trough right there at that one moment, and you could you could see how you could see how putting your hand or some other object at just the right distance in front of the antenna causes more absorption.
Yeah, it sparkles, as we used to say. I started out doing ultrasonic. Actually, I did something that's on cars today. It's an ultrasonic. We didn't call it a backup detector, but and what we realized was objects, just because of the normal little bit of motion, the different facets of the object sparkles, and it's picture a ball of aluminum foil in the sunlight. As you move it around, you'll see these real high returns every now and then. So you can use them or you can filter them out. It was what we found in the ultrasonic days.
now here, this all comes down to, you always, a lot of people see these PCB antennas, right? Now here's an inverted F antenna. I'll bring up a picture.
Okay, cool.
An image in new tab. Let's see if this works.
So somebody asked a question about a SID, but I don't understand. Oh, by Tim. Oh, yeah, I don't remember what by Tim means on the SID chip. I can ask somebody that worked on the SID chip.
Let me just share this real quick.
Yep, let me add your source.
Did you see this? You see this web browser window?
Yeah, here we go.
So this is a typical design of an inverted F antenna, right? And
right.
so this is quickly getting squirrely, but basically, this is probably not the best picture because the antenna itself is a polygon and it's not poured. That's why it looks like cross-hatched. Let me find, maybe there's a better one to illustrate.
Oh, we could talk about cross-hatching someday in PCB design.
Yeah, so
we used to fight over it, physically fight. Whoops, lost you. So while Ben is kind of frozen there, I'll go on to say that F antenna, that's typically, you might see that in Wi-Fi or in Bluetooth. There you go.
Yeah. So these are just the size for ISM band, so right around 2.4, 2.5 gigahertz. And they always have, I like this picture I found because it shows the point I was trying to make about that S11 is the antenna. What you can think of it is if you have a transmission line and you have a mismatched impedance, and I used the extremes of an open circuit or a short circuit before,
right? And
they give reflections, and you don't want reflections because it can cause voltage spikes at your source and can damage things, but also it means the signal's not going. It's not going where you want it to. It's just coming back into your source. We don't want that. We want the signal to go out and not come back. And so, but the impedance of air, electromagnetic waves traveling through air, the impedance is 377 ohms, roughly.
Right.
The impedance of our circuit board trace or the coax cable we use in an antenna is 50 ohms. So what is the antenna? When you have, I could have a 300 ohm trace on the board, but a 50 ohm source. So what do? I have to have a little component on the board that matches the impedance. And that may be literally a transformer with different windings on primary and secondary. But at 2.4 gigahertz and those frequencies higher, we actually use circuit board tapers. It's called an impedance transformer. And we use shapes on the board to do it. But what the antenna also is, if you think about it, an antenna is a transformer that transforms. It does two things. It radiates, of course, that's the primary job of it, but it helps us match a 50 ohm source impedance to the 377 ohm air impedance. So it's really a dual function device, if you think about it. That's how I think about it anyway. Maybe I'm way off. An RF specialist would tell me I'm on crack probably, or they might say, yeah. But here's the thing, antennas never match directly. Because of that, they never perfectly match directly to 50 ohms. So you have to have some kind of additional circuitry to match the impedance from your circuit board trace to the antenna.
Right.
And so that's why
it's all a compromise.
Yeah.
Right?
And so I don't think I've ever seen an antenna design that was naturally just 50 ohms. Have you?
I don't know that they exist. As you said, free air is 377 ohms, so you have to try and match to the air.
I mean,
right?
this Vivaldi antenna, this is a circuit board antenna, and I manually, okay, so it's somewhere between a slot and a dipole, and slots can be matched just by changing the feed position. So this one, I basically held the coax endpoint down with a piece of plastic on the VNA and sort of moved it till I found the sweet spot and then soldered it on. And so it is pretty closely matched, but
it's been tuned.
Yeah. And this is why I used to think those people that do microwaves and RF are kind of wizards, because they'll do crazy stuff like get a waveguide and they just knew where to tap, tap, tap and put little dents in it here and there to match. And
right.
it's like, how does one know where to hit? But I think it's knowing the physics and being able to visualize in your head what the waves would look like if you could see them. But it's also experience, I think. There's a lot of experience in this field.
Well, Mike just pulled off one. He mentioned the cable being part of this, and I had assumed I was using a good cable. I just swapped the cable for a very short one, and look what's happened to the display.
Oh, it looks very different.
It does. Here we go.
Yeah,
and there we see the actual, look at
resonance. Yeah, much better resonance at 2 different frequencies there.
Yeah, and we're all the way down to almost 35 dB of transference to the air.
So
that much less reflection.
So just to reiterate, if you're looking at S11, low is better.
Right.
Yeah, the ideal transmission line system and load or antenna is massively wide bandwidth and 0 reflections. So you have negative infinity S11.
So, yeah. Now, when I first got into this, I thought S parameters meant S like in Laplace transforms, and so I was afraid of them, right? Because I couldn't do Laplace. I didn't realize it's just an equation. I didn't know that imaginary numbers are a way to describe non-rational numbers. But then I'm like, a scattering thing. Wow, that sounds like something I can get my hand around.
Yeah. So, and that's the thing. You can't avoid some math, right? This is engineering after all.
It is.
But the math always looks hard when you've never done it. And then once you've had someone who's capable of explaining things, because let's face it, there's a lot of lecturers in a lot of universities who are primarily there to do research, and they understand the stuff sort of naturally, but they're not always gifted at helping other people understand it. And so just a side note, look for a college if you want to study engineering professionally. Look for a college or university that has teachers who are just super passionate about the subject matter, because then you'll have a far better experience learning it, rather than some of the schools are just primarily research and grant focused, and those ones have angry people who are frustrated all the time, who know the stuff better than anyone, but they can't explain it. So right. Anyway.
Very cool. Having never been to college, that was my impression from the outside as well.
Yeah, do what Bill did. Find good books and teach yourself, because very few people know something as well as the autodidacts. Jerry Ellersworth is another one of them. You know, my hat's off to anyone who can make her own MOSFETs in her garage. That's like, to me, that is mind-blowing.
Yeah, she showed me one of her, hang on. She showed me one of her transistors grown on a piece of glass and stuff. That was pretty cool. That was, that was 10 years ago now, I think.
So it's funny that fell off the desk, and as it was swinging, the S11 was dipping more and more there.
Right. Well, I was going to do what we were talking about, which is try and hook a second antenna up.
And see what the transfer is between them. So we want it. So that's looking at S21. So S21 is when you're looking into the transmission system from the receiving end. How much power is coming out of this compared to what's going in? That's your S21. And so you can test the effectiveness and
right, the transfer.
You can test the polar, you can generate polar plots and test the transfer characteristics of, two antennas facing each other. But of course, in that scenario, you're getting lost through the ether as well. But it's okay.
There we are, coupled antenna to antenna. There's my hand in the middle, and the signal goes down.
Yeah.
And there's my hand, and it's peaking right around the 2.5.
Because you have
right in here is around 2.5 gig.
Because you have mercury for blood, right?
I have water.
You're a metal man.
I have hydrogen-oxygen bonds that like to absorb frequencies in the gigahertz range, which is why the microwave oven works.
Especially with all that salt, you're very conductive inside.
Good point. Though, I've high voltage or RF burns, they find the path of least conductance, and a lot of times that's your bone marrow. It'll actually burn a slug through your finger into your bone marrow and travel down that way, and that's why it can be so insidious, is it can kill your bone marrow if you catch an RF burn bad enough.
That's really nasty. Yeah, I'd never even thought about that.
Yeah, at the trauma center, we had somebody with his heel. We knew to look, and his heel was burnt. And that's where whatever he had touched, and I forget what it is, may have been just regular old high voltage. That's where it exited his body.
Yikes.
Yeah, ow. He was conscious. He wasn't happy, but he was conscious.
So he got a shock. He survived. He was okay. His heart was beating, but his heel was really sore.
Yeah, and if it was RF, he may have had bone marrow issues or something.
Yeah.
So
things get squirrely at RF. High power RF is really unpredictable and dangerous.
Ionization and whatnot. So, isn't that how they rate transmitters, like your cell phone? They rate its safety on its ionization.
I don't know. I should know. I should look into that.
I believe it's the ability, its penetration and the ability to ionize, some molecule at some depth, and so I think I think that's kind of one of the things they key off of.
But wait, it's still below ultraviolet light. It's non-ionizing radiation, though, right?
I could be wrong, but I thought that's the parameter that you test for. For example, if you have something that's been tested for ionization and you combine it with another RF transmitter in the same housing, you're supposed to get it checked again, that they could have a nonlinear effect in the amount of ionization that they could create in the body.
I need to learn
I'm going off old burnout memory,
I need to learn more about that, because the bottom line is, even if it's non-ionizing radiation, RF at whatever power levels does damage tissue.
So here I'm sitting with basically a radar gun pointed in my lab. I should probably turn it off now, you think?
I'm sure it's pretty low powered though, right?
I'm sure it's pretty low power too. I won't set it in my lap or anything. They had a problem with cops when the first radar guns came out, the portables, and they were leaky and all kinds of, and higher power, and they'd set them in their lap while they were driving. As before we knew as a culture about not setting radars in your lap.
Yeah, so those cops only had daughters, right?
Well, is that it? Do you think it hits the
children?
Yeah, I was going to say, if any children. It's, in a way, it was kind of evolution at work, but, I won't say that in front of my cop friends.
I remember when my wife was a new mom with our oldest, and one winter morning, we had the house we were renting at the time had these steps into the backyard, and they were painted, and they didn't have any grip sort of material on them. And we didn't even notice. All summer was fine, and we would just walk up and down and never a problem. But this one winter morning early, I was on my way to work, and I get this phone call, and she was panicked, and she'd been carrying a washing basket down the steps, and there was a little tiny bit of frost or condensation or something, and she slipped and landed with the corner of one of these concrete steps right in the small of her back.
Ow.
And she was in excruciating pain, could basically not get up. I called around. I had some family members who were living close and had them go over and sort of help her get into bed and take care of our baby daughter at the time, and until we could get to the urgent care.
Yeah, and I was going to say, we would treat that with extreme caution. We would longboard on scene if we showed up as EMTs.
Yeah. So later in the day, she was actually able to get up and move around, but she was still in a lot of pain. So we thought, well, maybe she probably hasn't broken anything. She's just got a really nasty bruise. But then we went to the GP, and he used this device that looked like one of those really old school cop radar guns with a big round sort of dome front, like the ones they used to prop up on the side of the road in the early 80s. And he had something that looked almost exactly like that. And he's like, well, like, what is this? Is microwave therapy. We're going to shoot microwaves in, and from the inside out, you'll be warmed, and it'll, help your muscles relax and all of that. And she said it was just a really trippy feeling heat coming from the inside of you. And
how long ago was that? Because was that in the States? I haven't heard of microwave therapy.
That was in Australia, and that was probably 17 years ago. And she would never do anything like that today. She's right. She would look at that today,
especially while pregnant.
Thinks back, yeah. We'd had the baby, it was a few months old, but she would never do that today. She would think that is just insanity, standing in front of a high-powered microwave source.
Well, fluoroscopes. We had no idea what we were doing to people with fluoroscopes. Do you remember seeing those, the live skeleton pictures and whatnot? And basically, they're standing in front of a small atomic blast with a fluorescing material behind them, a fluorescing detector.
Yeah, well, I thought they had those as a test tool on Navy ships for detecting transmission. So in and around the radar dish, they would have little neon light bulbs, and you knew if they were lit up, you shouldn't be in the area, because they took all their energy from the RF. They weren't connected to any wires. They would just light up.
Somebody I knew when I was younger was in Vietnam, and they would walk out in front of the craft to test the radar. He's like, yeah, we did that without even thinking about it. You walk out 20 feet, and the guy says, yep, we got you. And that's how they tested their forward-looking radar,
So, Bill, I feel like in the dark here because I'm not on YouTube and looking at the chat there. What are people talking about?
I just see where it says transmissions are back, so I don't know if that meant that we went down or not.
It might have been me.
He's saying, neon tattletale. Didn't somebody... I'm trying to think if a story I heard is real or not. That's the problem when you get old. Somebody painted a radar dish with lead-based paint or something, and resulted in a small fire when they first... And we're talking like a shipboard radar or something like that, but... that may be urban legend. I can't remember for sure.
I don't know.
But it sounds like something the Navy would do.
Okay, I'm back on the tube on my other computer just so I can read through the comments and see what's going on. Mike, Coriolis effect is painful. Is it because my Skype calls keep dropping? Probably. I really need to.
I haven't lost you.
I need to do this on a mobile tether. I think that'll help.
Okay. I was going to say I haven't seen it. You've dropped a couple times, but it was just you that I knew of. But if we're dropping as a whole, that's a problem.
I don't think your streaming's usually pretty darn solid. You've got the network to do it.
Yeah. So. Hey, we were talking about the internet, and here's a book for you. This is what I used for knowledge before the internet, was books like this called The Way Things Work. And there was Oh, what was the name? Lucifer's Hammer. There was a book by Pornell and Niven, a science fiction book. I'm an old science fiction fan.
Lucifer's Hammer was a sports car, wasn't it?
Not that I know of. It was a meteor that hit the Earth. So this was way before the post-apocalyptic things. And one of the guys took all his books and put them in Ziploc bags and stuck them in his septic system, of all things. And they mentioned the book, The Way Things Work, specifically. And this is how, like, there, I just opened how a jet propulsion engine works. I mean,
I love that.
There's how, and look, they tried to put all the knowledge, there's how a car engine works, So it was great. This is what we did before. Here's how, there's ballistic projectile testing and stuff.
That's worth having for the illustrations, because I'll tell you what, even with Wikipedia, as marvelous as it is, and I love it, I'm kind of a Wikipedia junkie sometimes, right. But even with that, what I find is that the people, especially in science and technology, what I find is that an article will be written by someone who has a good practical grasp of the topic, and they'll write it. They'll write it so that a high school kid or someone else who's less familiar with it can actually learn from it and get a pretty good idea of how that thing works and what it is. And then it gets added to and added to and edited and edited. And over time, academics come in and add all the technically correct and very deep, detailed knowledge to the article.
Right.
And after about 2 or 3 years, it's impossible for any normal person to read anymore, because it's like a treatise on the subject, and they're showing all the exceedingly accurate, deep. And so I kind of lament that sometimes. There are things I want to learn about that are outside of my field, and I'll go look it up in Wikipedia, and 10 years ago, I could go to Wikipedia and I'd get a pretty good conversational grasp of the topic that would allow me to do things like this. But I go today, circular polarization one's one of the better ones. It's a better example of something that's more easy to grasp, but maybe that's because I'm an EE and I already understand what circular
but they did exactly what you
is.
said, was fill it so full of math that I wanted a good example to help somebody intuitively understand where the circular comes from.
Yeah.
And it's full of, and it should be full of math, but it's kind of an example of what you're talking about.
There's a far better way to learn things like this now, really, is things, well, in that particular, if we're talking electromagnetics, you're better off starting with watching some videos on YouTube done by radio amateurs. And then there are some lecturers. This one particular guy who I think is at the university, he runs a computational electromagnetics lab at the University of El Paso, Texas. And I don't remember his name right now, but he has, all his lectures are on YouTube, and they're all, some of them are undergraduate level, some are at graduate level, but they're all, like, he just has this amazing ability to explain things in a way that's just visual, and he writes these Python, or I guess he's using there's a Python library for visual.
Oh, there's computing. A wonderful Python library for that kind of stuff. Yeah.
Yeah, it was written by 3 Blue 1 Brown, or 3 Brown 1 Blue, whatever. That guy has all the YouTube videos on math topics, who's really amazing. His Python library. This other guy, I think it's Raymond Rumpf, or I think it's Ray. I think his name's Raymond. He's a computational electromagnetics professor, and he just has this beautiful way of explaining things in his decks that's very visual. So that's kind of what I've turned to. In Wikipedia, once I've learned something more deeply and I need more of the technical and math side of things, Wikipedia is good for that, because that's sort of how it's gone.
Right. Yeah, I meant to show my Radio Amateur's Handbook today, but it's upstairs. I didn't want to run all the way up there while you were talking. But that was on my list of things to show, and you're absolutely right. It was the hams doing this. Hams could see RF before I could, is the way I look at it.
And if you want to learn antennas and polarization,
oh my God, yeah,
go to arrl.org, join up, and buy the books. There's a 4-volume set on antennas that lays everything out, and it gets as far as what professional antenna designers would use, but it's approachable to anyone who has high school level math. So it's just awesome.
Cool.
They don't talk a lot about PCB antennas because hams don't normally use PCB antennas, but I think that's changing. If you want to build a Vivaldi antenna, it's going to be on a circuit board substrate. And by the way, a Vivaldi antenna is this slot, right? And it's this horn shape is that's exponential. So you can't just make that shape. I see people designing Vivaldi antennas in PCB tools just with arcs, but the arcs are circular, and this is not circular. This is this is hyperbolic, an exponent. It's exponential, and so you need to write a little script. I wrote a script to make that shape based on some input parameters. But the thing I love about Vivaldi antennas and why I think they're going to take over is because they're so wide band. They're so wide band. Like I can make this one antenna. This is I think also ISM 2.4 gigahertz was the center target frequency, but it's so wide band it'll go down to 1 gig and all the way up to 6.
Right.
With good matching. So that's why we use them, because you can make one antenna for many different applications.
Now, tell me more about that script. You wrote the script in what, and then how did you translate that into a PC board?
This particular one was I did design this while I was still working at Altium, so I used the scripting engine in there. And I've found since then someone has also written a ULP for Eagle, which would also work in Fusion Electronics. Because it's just simple math, and all it has to do is create a polygon, really an outline in copper of that shape, and then you fill it in with a polygon. It's pretty easy. The hard part is if you're doing this on a board, you need to feed the antenna, and this one, because it's on a cable, I just soldered the cable straight onto the appropriate feed point. But normally a Vivaldi antenna has a feed line on the backside, but this is not a double-sided board. And the feed line comes up and goes across, and you have to experiment a bit with where the copper should go. So the backside of it is a microstrip line, and it's terminated with a little stub under the slot, and the signal radiates into the slot from the microstrip line, and then resonates and radiates out of the slot. Oh, that's it. That is a heck of a Vivaldi antenna. That's beautiful.
That's 900 to 12 gig, 900 megahertz to 12 gig.
See, and that's precisely why we use them. Such wide. They're very, very effective radiators with extremely wide bandwidth.
And they can be made on a PC board.
Yep. Unix 1286, every science or technical book I Google looks like it's for kindergartners. Well, I guess you're from Gallifrey and have 2 hearts and live multiple lives. No, I'm just kidding. There is a lot of stuff out there that is I think that's right. There's 2 levels that we seem to find in books. They're either really, really ultra basic or really, really deep, like academic, and no sort of good middle ground that walks regular engineers into knowledge of new areas that they haven't studied before. I think that's why we like some of the older books, hey Bill, because they present things in a more intermediate way.
Right.
At least that's my opinion.
I learned from books like this.
Yeah.
This is Signetics. I've been throwing around a lot of Apple, jeez. a lot of national apples
Whoa.
on my mind.
That was Freudian.
Yes, it was. We were just talking about who sold more of what.
Has the eye cult gotten into your head?
Yeah. Oh yeah. Pretty soon, the whole thing of experts and stuff, right? Being a self-created category.
By the way,
but no, I learned face lock
for the record,
loops.
everyone, I'm a huge fan of. I don't use modern Apple products much. Some of my family members do, but I'm a huge fan of Wozniak. Like every engineer really should be, if you think about it.
I'm not.
You're not?
No, I didn't get along with him.
Oh, really? What was that,
Yeah.
Bill?
I won't talk a lot about it. He probably doesn't even remember me, but no, it's and I had to go to Chuck Peddle, the guy that did the 6502, and I explained the story, and I'll tell you offline. But he said, "Oh, that's because," and he tells me why Wozniak didn't get what I was talking about, but
well, I'm sorry.
If I'll fill in part of the story. When we were talking, he used the phrase "change the world" 3 times in 2 sentences, and he get this lofty gaze, and I'm like, I was just trying to get product out the door, dude.
Yeah.
So we were on opposite ends of the change the world spectrum.
But dude, where was MOS Technologies headquarters? Chicago? Where is it again? It's in your. It's in
King of Prussia, Pennsylvania was where it was.
Yeah. So that's the difference between Pennsylvania and San Francisco.
Oh, they moved Commodore to the East Coast for that. You could hire good engineers a hell of a lot cheaper, and we were a different category. You could get somebody like me who would burn down the house to get done on time.
Yeah, it's called commitment-based engineering. That's another topic that's interesting for maybe another day. One of my friends and one of our engineers pointed this out to me in a meeting early this morning. He sent me a link to this really fascinating article on the difference between process-oriented versus commitment-oriented. And
right.
I think there's nothing really wrong with being process-oriented, and a lot of businesses do business just fine that way. But there's this thing about hardware and inventing new hardware that, particularly for people coming up with a new sort of hardware idea, like back then it was the personal computer, but today it's assistive devices, or it's VR was a more recent one, and AR. But not a lot gets done without that kind of level of commitment from the people doing it. They're just super passionate, and they're willing to say,
we were willing to kill.
I will get this done one way or another.
and that was the Jack Tramiel culture as well. He wouldn't forget, if you had made a commitment, you better come through on it. And we could have blamed in the 128 or the TED, we could have blamed the chips and just thrown our hands up. And we didn't. We found ways to make the chips work. In one case, we phase locked one to the other one because the guy hadn't tried to fix synchronicity issues. And it just didn't work. Not even in...
Did we talk about clock domains already in an episode?
We didn't, but they were 2 different clock domains.
Yeah.
And the guy didn't even...
What's a clock domain?
Oh, I'm going to let you handle that. A clock is a known set thing, and it's synchronous, and any event derived from it will be synchronous to it in some way. It will not move on a screen one by the other if you had 2 traces on an oscilloscope. A second clock domain is asynchronous, which means any available combination of timing could happen and will happen, usually in the course of a couple seconds. And if you are counting on things like data setup time, if you have a clock edge and the data has to be, well, no, the data is asynchronous. It's moving all over the place. And I used to say it's like launching yourself towards a revolving door with an armful of packages, and only the packages come out the opposite side. You got to time it so that you and the... Yeah.
But I wanted to just put a pin on that because that's a big problem in modern systems. If you have it's quite likely people watching this are going to design something where you have, I don't know, you have an Atmel 328p microcontroller and it's measuring stuff and looking for incoming signals, right? But it has its own internal clock. But then you might on the same board have an ESP32 and you might wonder why your application software tends to work while you're in debug mode, but as soon as you go into release mode where it's running at full speed, things every few seconds, the thing loses, like it goes off into la la land and you can't figure out why. Often it's this kind of clock domain problem where you're sampling data on one device and its clock is not synchronous to any other device on the board. So how do you deal with that? How do you solve that problem?
And you can't perfectly. So it's about statistics, and it's basically how you condition it. You run it to a flop, which runs it to another flop, which runs it. So you exchange delay for statistics.
Right. So you have. So what you're saying, and do you have your notepad there? You could draw this. I don't have a notepad set up here. I keep meaning to set up my digital pen so we can use it. Maybe next week I'll do it. So you have your incoming signal sampled by a flip-flop, and the flip-flop's running to our local clock, right? And then you have at least one more flip-flop, but often 3 is good. And they're all sampled to the same clock. And then the input of one goes to the output of one goes to the input of the next, and so on. So you sample it 3 times. Right. So if you get
or 7 or some number, depends on what you're after.
Right. So if you happen to sample a signal right at its undetermined transition state,
you'll go metastable, which means it's an unknown state, and you start to propagate an unknown state.
Yeah, but what you then do is you have an AND gate taking all those outputs together and basically summing them. And when they all agree, that's when you get your synchronous logic 0 to logic 1 inside your chip.
Right. And that's all he would have had to do.
Yeah.
But this chip designer, and this guy had patents on the old 68,000 processor. He was brilliant, right? But he missed the real world aspect of this exact conversation we were having. And he said, well, even 7 will still statistically fail. So you know how many he put in? None. And so it blew up every time we loaded the font ROM. And so what I did was, this is 2 weeks before a CES show, I developed a phase lock loop tower that slid under it, and it took the 8.18 megahertz dot clock that we used for the dots on your screen, and I made a doubler out of it. Now, it was more convoluted than that. It was like 5/8 times 14.318 or something like that. But it was a true.
But you did that analog, like old school, with a PLL. You didn't do it.
I did. I used a CD 4060, 4046, whatever that one is, that old CMOS one. Yeah. I love that thing. It's got 2 different types of input, phase detectors. And we built it on a board, and then I had a delay line after it, and I left one wire where I could move the wire between these delays, so it was like adjusting the dwell angle. Because we didn't know what the chip wanted, right? Nobody knew, including the chip designer, and we found about the 5th tap worked every time. And that's how we went to CS shows. And those boards, this big, cost $1,000 each, because we had them made in 8 hours back in the 80s.
Wow.
So we all stood around with coffee cups listening to the news on the radio, in case like the guy gets in he's on his motorcycle to pick up the boards, and we're like, going, there's a horrible accident on Route 202, PC boards everywhere on the highway. It's
But I'm surprised you guys didn't have your own board fab in-house too back then.
Geez, as it was, we had to wait a week or two. When I started there, we didn't even do our own layout. I had to go to a company called 4th Generation in Bristol, Pennsylvania, and it was all hand tape. And then I got a friend of mine, Fish, came in, and just at the time we got SiCards.
Right.
And so But the sidecards is more. There was no design rule check. I mean, you still had a.
It was
I
all
shouldn't say that.
grid-based.
Yeah, you had to.
Every trace and space relied on you doing things to a grid.
It wasn't gridless, right? And you had to hand type in the net list, so you would sit there and take turns. One guy inking the schematic while the other guy read the net list, and then you had to do the net list to the layout sometimes if it broke the database, and it was it was not for, but we got it done, right? And it was only 2 layers too. That helped a lot. Yeah. And we couldn't even afford a 4-layer board. And I mean, even at Commodore, we couldn't afford a 4-layer board for anything in production except the business machines.
I remember when I was first into electronics,
1 clock to rule them all.
Even 2-layer boards were, even in the mid-'80s, 2-layer boards were rare. People avoided it because the cost of 2-sided and through-hole plating back then was really high.
Right. Yeah, we used to use insertable through holes back when I first started.
Yep. Yep.
So the
little spigots.
So Mike made a joke about 1 clock to rule them all. So I did a design of a video concentrator one time where I had 16 cameras I designed the cameras using CCD image arrays, and they derived their clock from this camera concentrator. We called it a CamCon. And that clock had exactly 1 oscillator on it because I was never, ever in my life again going to deal with asynchronicity if I could help it. So I would stand there in front of this huge installation with all these cameras and everything, part of a security system. Actually, it was object recognition. It was pretty interesting stuff. We got a patent on it. But I could sit there and I would tap on the 1 oscillator, and in my mind, I could see all the cameras vibrate, right? Because they're all derived from one, in the micronics, that little bit of physical force you do when you tap a crystal. It will change its frequency so I would tap on it just to we're all on one domain. Thank you.
Yeah. Caps. That's another plague of high gain audio. If you wanted to design a preamp for ribbon or gold sputtered diaphragm microphones, you need ridiculously high gain, and you need ridiculously high input impedance.
It sounds like a tube.
Those 2 things are a stupidly difficult combination to design well for. So you might have a FET or tube gate input, a tube grid input or a FET gate input.
And it had to be close to the mic. And
you have to bias the mic to a very high voltage power supply that has to be squeaky clean. And the reason it has to be so high voltage is to get the high impedance. You need a very high, multiple gigohms input resistor, bias resistor. And then you have this problem that you can, on the other side of the FET, you have capacitors that couple to the driver stage. But you just tap those capacitors and you get massive bass spikes coming out of your system. So
okay.
It's
what was there was a tweeter.
This is why high-end analog audio companies like Lynn in Scotland make turntables with granite.
right. Or now float on magnetics. They go the opposite way too, right?
Yeah.
So what was I going to so there was a high voltage speaker technology out that I saw exactly once in the 70s. And I think they called it a hydrostatic tweeter. So
electrostatic speakers, and they could do full range, including bass as well. And there was even I think it was Electronics Today International, which was an Australian-based electronics magazine back in the 70s and 80s, had an actual project where you could go to the hardware store and buy all the parts and buy copper foil and films and make yourself a set of these. The main electronics project was the high voltage amplifier to drive them. Because we're talking kilovolts. You need kilovolts.
We are. We're talking get hurt by your speaker.
Yeah, don't stand too close to it.
Yeah. Well, and that was something I had a good teacher. I did have one electronics class, which was a Votech TV repair class. And I learned how to deal correctly with high voltage. And so I have no problem sticking my hand in the back of a TV set. And my hand will automatically go behind my back when I lean forward to this day if the set's turned on.
Yeah, and you take any jewelry off.
I only ever wore one piece of jewel my entire life. It was my wedding ring, and I lost my finger due to it. So that'll teach me. That's not true. I wore dog tags, but we those to take off, right?
Yeah.
When I was in the service. So I'll tell, to wrap up here, I'll tell a story about high voltage if you want to hear.
Yeah, yes, please.
Okay. So the guy's name was Larry Davis in Marion, Indiana. He was the Votech TV repair teacher. And he taught me to shut up and figure it out. That was the biggest thing he could do for me. Well, he had like some number written on the board, like 12 or something with a circle on it. And we'd say, Mr. Davis, what's the 12? What's that? And he wouldn't answer. He'd act like he didn't even hear us. Then one day you hear, pow, ah! And he called everybody over. And he's like, how you doing, Jimmy? I don't feel good. You don't feel good, Jimmy. Tell us what you did. I didn't discharge the picture tube before trying to change the damper. You didn't discharge the picture tube before changing the damper. He walked over to the board, erases it, and it became whatever the next number was, a 13 or whatever. And that's a true story. And so then we're all sworn to secrecy. We can't tell the next class what the number means, So that's my high voltage story. And I never got hit by the voltage. A friend of mine got hit once and put right up against the wall because his legs straightened out, when he, and it projected. They said he looked like a jack-in-the-box popping up behind the TV.
You're just as likely, you're more likely to be injured from the reaction to the shock than from the shock.
Oh, you hurt yourself, yeah.
Yeah.
Yep.
I did something similar once. The first serious the first moderately difficult electronics kit project I put together as an 11-year-old was a strobe. A strobe light.
Yeah.
With a xenon tube. So it had 370 volts DC on the inside of it with big storage caps.
Right.
And a 4 kilovolt trigger transformer. And I was busy showing off the insides of it to a mate of mine while it was turned on. And I was saying, so the power comes in here, and I was pointing with my finger, and I made that one false move where my finger touched the DC rail, and my arm just immediately flew back.
That's what happened
involuntarily, and my whole arm was aching.
Yeah,
super
so
embarrassing.
That's how I learned about capacitors. I opened my dad's strobe light. And I put my finger down next to the xenon tube because the 3 terminals, and one, as you know, the center is the trigger terminal, and there's voltage still on the caps. And when my finger shorted across those, it blew my arm back behind me. It's DC on top of everything else. And I remember going, oh, those big blue things are like fast batteries. And that was how I first started learning about capacitors. So... All right, camera flash.
You get into the practical jokes where you pre-charge a DC cap, and your friend walks in the room, and you throw it and say, "Hey, catch!" and they go instinctively.
We had a rule around me. It says, "Do that and get your ass kicked." And I even had a Votech teacher throw me a cap from like the condenser cap from a small motor, and he saw the way I caught it so that it, I didn't catch the terminals. I looked at him and said, you would never charge a cap and throw it to a student. No, I didn't say student, but a person, right? And he looked at me and said, I saw the way you caught that. Yeah, no, I would never do that. But, that in flight, my mind's going, could be a charged cap.
Yeah, you've bit that one before.
Yeah, I did. Yeah, especially you see somebody else get hurt, you don't ever want to yourself. We could talk about electric fences. They're fun, too, some other day. Yeah. Well, the trick there is to get somebody else to try the experiment for you if you think like an apple core will insulate you or whatnot. So.
Just don't whiz on it.
Hey, good seeing you again, my friend. Glad we were able to hook up. And we'll see everybody next week. And as always, we're on Discord. We're looking for topics. We didn't really talk about grid dip meters, but I brought mine out.
We can talk about that next week. We have to make sure we don't forget this time. Yeah.
Well, my battery was dead. I never even thought to try it, so it no loss there.
Cool.
So, all right.
Hey, good to
good
see
seeing
you, Bill.
everybody.
Good hearing from everyone. Thanks for joining us, and get on the Discord, and so
Get on
we
the
can
Discord.
stay in touch all week long.
So you go to Coriolis-effect.com and click on Discord there, and that's the invite. So you can get right.
Yeah, and Coriolis Effect is CORIOLIS -effect.com.
Yeah.
Cool.
So,
hey,
all
thanks,
right.
Bill.
We'll see you next week.
Bye.